the topic is circuit protection. Now, what we're doing here today is dangerous. And what we're presenting is presented in good faith, and it comes for a lot of time doing all sorts of protection circuits. However, if you blow yourself or your very, very special loco or your controller up, then that's on you. I'm not accepting responsibility for anything. I don't even accept responsibility for what I do. So you're basically on your own. We're going to talk about over voltage protection. We're going to talk about over current protection. We will also briefly mention over temperature protection. I am not going to talk about personal protection. That might be a discussion for some other time, might even be a discussion for some other buddy. It's an area that we should maybe explore at some point. I will also not be particularly going into the idea of monitored protection, where you have a processor looking at something and deciding to switch it off or anything like that. I'm more interested here in simple 1 and 2 and 3 component circuits that make your equipment safer from overcurrent or over voltage. We will be talking about both primary and secondary circuits, primary being on the mains side, so that you don't get mains electricity coming where it shouldn't and hurting things, and quite a bit about the secondary side, which is where we tend to be interested. The philosophy of protection is, first of all, if you can limit the thing that you're trying to protect from, if it's voltage or current or heat, limiting it is good. If you can't limit it, then divert it, make it be somewhere else where it's not going to do any harm. We always use the phenomenon that we are protecting against itself. Every one of the phenomenon has side effects. Voltages cause electric fields, voltages cause currents to flow, currents cause heat, heat causes melting. There's always a side effect that you can use to detect the phenomenon and use it to implement protection. We'll be using mostly just Ohm's law and Kirchhoff's law, a little bit of geometry, but we will depend almost entirely on something called a non-linear effect. Now that is where we go next. Non-linear devices are things that don't respond in a straight line. It's not a case of the more of it you do, the more it changes. So an inductor or capacitor, for example, at DC, an inductor is a short circuit. At AC, an inductor can be practically an open circuit. A capacitor is an open circuit at DC, but it becomes more or less a resistor when the frequency goes up. NTC and PTC resistors, that's negative temperature coefficient and positive temperature coefficient resistors. We're going to spend quite a bit of time looking at them in the next half hour or so. Semiconductors have got a non-linear response. That means that the resistance of a semiconductor keeps changing depending on what you're doing with it. Mechanical devices are mostly digital in their response. Switches, relays, things like that are either on or they're off. And that's non-linear. You know, it's not a case of you can have a switch that's more and more and more on. The switch is either on or it's off. And tungsten filament bulbs, which get forgotten about, but are wonderful devices. So much so that that's where I'm going to start, the humble bulb. There is a humble bulb. Over to the right-hand side of that picture, you will see a 12-volt, 5-watt side light bulb of a 1978 MGB. It's in a batten holder that's from 1968, I think. And I think the multimeters are about the same age. What we have there is a power supply at the bottom of the page, driving the bulb through the milliammeter. And the voltmeter is directly across the bulb. So I've got a bulb and I'm putting a varying voltage in it and I'm watching how much current flows. And there's what happens. The graph that my head's in front of doesn't matter so much. The other two do. As you can see, as the voltage goes up from 1 to 15, the current goes up. Nothing new there, nothing great, nothing serious to look at. But what happens is if you divide the voltage by the current, you get the resistance. Yep. Ohm's law, voltage over current equals resistance. And at 1 volt, the resistance of that bulb is 10 ohms. But at 10 volts, the resistance of that bulb is nearly 40 ohms. And at 15 volts, it's 45 ohms. So what happens is the resistance keeps changing as the voltage goes up and as the current goes up. It looks like it's nearly a straight line. Looking at those graphs, you think, well, they're a wee bit lepto, but they're not particularly off the straight. But if I compare it with a resistor, move my head out the road there. Okay, they've got a different resistance, so they've got a different slope. But if you look at the resistance of the resistor, it's a straight line all the way. It's 22 ohms all the time. Whereas the resistance of the bulb keeps changing. So that's what's called a positive temperature coefficient. And here's a story about that. 1937, a guy called William Hewlett, did his PhD at Stanford on nonlinear resistors in amplifiers. And it turned out you could make an oscillator that you didn't have to keep tweaking. So him and his pal, Dave Packard, started a wee company in their garage called Hewlett-Packard. And that was their first product. And it was an oscillator based round about having a bulb in place of a resistor. And if you put a bulb in instead of the resistor, this thing no longer drifted and it stayed at the same frequency and it stayed at the same outlet. And that was fascinating. They called it the 200B so that people wouldn't think it was their first product. And the B was so that they wouldn't think, so they would think it was the improved version. And they went for it. Walt Disney were rolling out their new movie, Fantasia, and they needed to set up the audio systems. Fantasia was an audio extravaganza, and they had to set up the audio systems in movie theaters up and down America. So they bought 8 of these boys at $71 a pop, and that's what started the Hewlett-Packard company. Walt Disney buying 8 of these, and the guy had did it because he worked out that a bulb is a bad resistor. The positive temperature coefficient resistor I just mentioned is one of 2 flavors of thermistors. You've maybe noticed this little symbol on circuit diagrams, and people always think that thermistors are for measuring temperature. They think, well, that's what these things are for. You put them in a circuit and they measure temperature. The real problem, though, is that thermistors are actually rubbish at measuring temperature, because a thermistor, as it measures temperature, it draws current. And as it draws current, it gets hot. And as it gets hot, it measures a different temperature. And its current changes and it measures a different temperature. So actually getting a thermistor to measure temperature is really quite the trick. They are used a lot as inrush limiters and as voltage suppressors, depending on whether they're NTC, negative temperature coefficient, the wee slope's going down, negative. Positive temperature coefficient, the wee slope's going up. A negative temperature coefficient device, that means that it's got a high resistance when you switch it on, and then the resistance gets less and less and less and less as it heats up. So that'll stop the inrush of current. If I've got something that's got it's nearly a short circuit and it draws a lot of current, if I put an NTC resistor in series with it, then when I switch it on, the NTC is a high resistor. But as it starts drawing current, the NTC's resistance will go down and down and down and down, and my circuit will get more and more and more and more of the current that it needs. So it gets switched on gently, it gets switched on softly, soft start, if you like. The PTC, the positive temperature coefficient, on the other hand, does the opposite. You put that across the circuit, and if the voltage goes high, this thing suddenly passes current, lets the current go away. And those things turn up practically everywhere as what we call VDRs, Varistors, VORs. You'll find these inside practically every power supply. The metal oxide varistor, they're actually an exotic semiconductor. They're designed for voltage suppression, and they're blue. They're always blue. I don't know why they're always blue, but blue is what they always are. Right? And if you look in the back of any power supply, any connection to the mains, you will find these blue, round blue boys, 20 millimeters in diameter, hanging about there. They behave at high voltages. If you look 250, 300 volts before they start to change. They're linear up till then. They're just a very high resistance up until about 300 volts. And then they become a very small resistance all of a sudden. And they will respond in 20 microseconds. They're designed for when you're sitting there trying to get your local to work and that bugger Craig switches on his log splitter with a big motor in it and you get a spike through the mains. This detects that and stops it from destroying your controller. Or you get a lightning strike 400 miles away and the mains all gets a bit of a bump. This will deflect that. It will stop that getting through to the input side of your circuit. They're energy limited. You don't rate these by voltage or by current. You rate them by energy. Now, energy is power times time. Power is current times voltage. So the rating for a varistor is the voltage times the current times the time. So you get them rated in 500 millijoules and 750 millijoules rating. And that means that one of these will, for example, suppress 600 volts for a quarter of a second. And the same device will suppress 60,000 volts for a 400th of a second. But it won't suppress 60,000 volts for a quarter of a second. It's only for a certain amount of energy. They will absorb an amount of energy, dissipate it as heat, and help the circuit downstream survive. Apparently, the crystal structure of them wears. Every time they are used, they wear. And eventually they wear out. But there's no knowing that they've worn out. They don't go black or fall off or any of that stuff. They just sit there looking at you. They're very, very difficult to diagnose if they're good, bad, or indifferent. But you have to put them in because very often, if you're designing a piece of equipment, you have to meet the UL spec or the CE spec, and those specifications will say that your device has to be able to withstand a 700 microjoule impulse, or a spike that lasts for up to 35 microseconds. And you have to actually put these devices in to pass those standards. But they're quite an exotic thing to be designing in. They're not something that you can just say, oh, well, it's a 1N40, 148 because it's going to be passing 1 amp at 120 volts. This is a wee bit more technical and a wee bit more specialised. They're there to stop inrush. And I'm going to tell the Scott Mueller lightning anecdote. Scott Mueller is, I don't know if you've ever seen the Davy Dick book, not the Davy Dick Merg, Davy Dick Model Railway book. There's another Davy Dick book that well, there's two other Davy Dick books. One he never mentions at all because you can only get that in the top shelf of Menzies. The other one was a blue book that went through the education system a number of years ago. And there's another American version of a very similar book. Here by a guy called Scott Mueller, called Upgrading and Repairing PCs. And this was the definitive manual for upgrading and repairing PCs. For 20 years or so, you got this. This was 4 inches thick at one stage. Great big book about every aspect of computers. And that was fine. I was in the college one day and they were throwing out one of the old versions. We were currently on the 18th version or the 19th version, and here was the third or fourth one going in the bin. Did I want it? And I thought, oh, I'll take it. So I'm flicking my way through it. And there's this story that Mueller tells about how early days he had a lab set up with half a dozen PCs all set up on it, all working away, and there was a bit of a lightning storm. And he lives in Ohio or Omaha or one of them flyover states, and they get lightning storms, and you've got long power lines there. And so he got a lightning strike in the mains. And of the 6 PCs, 4 of them, the power supplies were destroyed. And the 2 that weren't destroyed, he noticed, were the 2 where, you know how we all use the kettle lead to plug, and it's about 1 meter long. And in these 2 computers, he hadn't used the meter long kettle lead to plug into the supply. He'd run out of them. So he had a couple of 5 meter long ones that he'd coiled up and tied together with tie wraps and put into the back of the PCs. And that coiling up was sufficient of a choke to stop the inrush from the lightning strike, and these 2 machines survived. Now, it's not a definitive scientific study, and he says that himself in the book, that it's maybe just a coincidence, but it's worth thinking about. All you need to stop inrush is an inductor, although the NTC solution is also good, as I explained earlier on. The other side of the coin is sometimes you want inrush. So that's why I've put this up as a reminder as well. Many of you will remember old cathode ray tube televisions. In the 60s, you could take a magnet and hold it up to the television and distort people's faces. But then when colour television came in, they discouraged that, because in a colour television, the signal, the current that was going to the front screen went through a big metal mesh called a shadow mask, and the shadow mask could become distorted by magnetics. It was made of piece of fine steel, and if you put a magnet anywhere near it, it would distort, and from then on that screen would always have that bloom on it. So they didn't want you getting anywhere near the shadow mask with a magnet. But also the shadow mask had a large current going through it because of the actual current that was making the screen glow, and so for that reason it could become magnetized. So in order to stop this, they had a coil of wire around about the outside of the cathode ray tube called a degaussing coil. And it was connected straight across the mains via a PTC, positive temperature coefficient resistor. What happened there was when you switched on, this thing let current flow through this, and you got a huge current round about the screen to degauss it. But as the current flowed, the resistance of the PTC went up and up and up and up, and the degaussing current became less and less and less, so that by the time the heaters on the screen had hit up and the screen was actually coming on, the degaussing phase was finished and you never saw it. But you knew it was there because when you switched the TV on, it used to give this thump as it came on, old colour television sets, and that was the degaussing happening. And now at this stage in your life, you finally understood why that happened 40 years ago. That thump was a degaussing circuit that they used to put inside televisions. And if a circuit is failed, if a circuit is short, you will get an inrush and you have to deal with it. Sometimes the gods are good to you. Right? I was about to start explaining the next thing, and last night I was watching the Hornby Model World thing. Is anybody watching the Hornby Model World programme? And I'd been out on the back step through the week taking a picture of a piece of equipment of mine to put in this presentation. And my wife had said, "What's that for? Why are you using that? What is that about?" And I'd explained it to her, but I don't think she believed me. And we were watching the Hornby Model World thing last night, and this boy comes on And I said, see if he plugs that red thing into that blue thing, all the lights are going to go out. And she said, what? And just at that, he plugged the red thing into the blue thing and all the lights went out. Laugh, I nearly opened the drinks cabinet. There's mine that I was taking a picture of through the week. It's called a Variac. It's a variable auto transformer. And it's a marvellous thing for test equipment. That's next to it, in case you're interested, is a 15 amp, 27 ohm resistor, just in case you've never seen one. This is my weightlifting collection, by the way. The Variac variable transformer is a wonderful thing. What it does is it lets you bring the power into a piece of equipment up very slowly, very gently, so that instead of putting the full mains on, you can bring it up 40, 50, 60, 100, 120 and see if something's going to smoke or pop or burst into flames or whatever by very gently applying the mains power. If you're using it for that purpose, then you want the Variac to have a low rated fuse in it, so that if your equipment suddenly starts drawing a lot of current, the fuse pops. But when you switch the Variac on, it's a great big coil of copper wire straight across the mains, so it will blow the fuse. Yeah. So what you've then got to do is put a big fuse in it so it doesn't blow the fuse. But if you put the big fuse in it, you don't get the protection when it's running, when you've got your equipment on it. So you want to have two fuses on this, basically, one for when it's up and running and one for when you're switching it on. But of course you can't switch between the fuses because that would involve switching, in which case you would blow the fuses. So the trick that I have used on mine is to put a lamp in series with the Variac. And if I go back to that photograph, you'll notice that there's a bulb there. It's not just putting the picture for scale. That bulb is actually a 60 watt bulb in series with that Variac. What happens now is when I switch that Variac on, that bulb is effectively, the Variac's a short circuit. So I've got a 60 watt lamp across the mains, so it lights up. And then as the Variac charges up, there's less and less voltage for the bulb, and the bulb basically dims. It takes about 3 seconds to dim, at which point my Variac's on and I'm off. I'm away to the races. But when you switch it on, that bulb goes bing. It one, tells you you've switched this mains on, watch you don't lick anything important, and two, it protects the Variac from damage, and it means you can use a 3 amp fuse or a 5 amp fuse to protect your circuit. That idea of an inductor is used a lot. And what you do is you wind the inductor against itself so that the mutual inductance is pushing against the inrushing current. As the current tries to increase across that inductor, the other side of that inductor, it will resist the changing current, but it will release it very, very gently so that you will get less inrush. And this here is called a common mode choke. They're very often toroidal in nature. You get a little round ferrite donut and you wind both the windings of the choke onto it over each other, or you put something called a bifilar wound coil on there and connect it. We'll leave bifilar wound coils are beyond what we're talking about today. And that there is a fairly good inductive protection system. It's got a noise capacitor. It's got a resistor to bleed any energy out of that capacitor and out of that choke. Any capacitor that you put across the mains has to be X rated. Got nothing to do with porn. X rated means it's rated to go across 450 volts. Anything that goes beyond at the input side, beyond the inductors, has to be at least Y rated, which is 400 volts. And these things have to be the white capacitors with the X and Y rating on them. And so if you start trying to buy all that stuff and specify it, it's starting to run into money, but you don't need to. This is from the Schaefer catalogue. Schaefer make a lot of this good stuff. And these cost about £4. And basically it's a kettle plug type. Actually, it's an IEC 10 amp connector with spades at the back for live, neutral and ground, and your connectors over to the connector for the kettle cable over to the left there. Two types here, the R&Bs are both got a resistive bleeder, whereas the Z type has the NTC varistor in circuit to stop inrush. And suddenly this stuff's starting to make sense. Moving swiftly on to the secondary circuit, much more interesting. Get away from the weightlifting. I'm going to move that good looking fella back over there. The simplest way to stabilize a secondary voltage is using a Zener diode. We've probably all come across this. I know Davey covers it on the electronics course. If I have 3 volts at the input there, there'll be 3 volts at that diode. 4 volts, let's say that's a 5 volt diode. Then at 3 volts, 4 volts, 5 volts, there'll be 3 volts, 4 volts, 5 volts coming out of the diode. At 6 volts, 7 volts, 8 volts, there'll still be 5 volts at the diode, but there'll be the difference, 2 volts or 3 volts or 4 volts across that resistor. And so I'll get a stable 5 volts out of that circuit at the right-hand side. The problem with that circuit is that all the current to go to whatever it is I'm using has to go through that resistor. So that has to be a big, beefy resistor. And at the same time, if my circuit isn't drawing current, then all the current that my circuit isn't drawing has to go through the diode. So I need a big, beefy Zener diode, and they're money. So the best way to get round about that, time again, is to use a transistor in the tail. In this case, it's the same circuit, except for the output voltage is a tiny wee bit less, 0.6 of a volt less. But now only 100th of the current goes through the resistor, and 100th of the current goes through the Zener diode, in which case nearly all the work's done by the transistor. And a big beefy transistor like that only costs, you know, £1 or whatever, and that's a good solid voltage stabilizer. But it's not a regulator. It'll set the voltage and it'll keep it there. If the current drawn by my circuit goes up or down, then the voltage there, as the more current's drawn, that the output of that transistor will droop. In order to actually regulate the voltage, what I have to do is measure the voltage at the output using a resistor ladder and feed that back to a difference amplifier. And the difference amplifier will take the difference between what it's set at, which is set by the Zener, and what it's actually there, which is picked up by the ladder, and it will turn the transistor on and off. And that's what's inside a voltage regulator. And we're all met voltage regulators. The 7805 and the 78L05 and the L1117 and all these things that we put onto boards all the time, and we use them as jelly beans. And oh yeah, you just simply put in a capacitor and then a regulator and you're off to the races. Turns out, as a design perspective, it's a wee bit more complicated than that. There's the circuit that we all know and love. And I'm going to move through it from left to right. We assume that we've got AC going into the bridge rectifier, typically from a transformer. So the output of the bridge will look like that. The input's in blue, the output's the rectified output, so-called full wave bridge rectifier. And you get these lumps. To get the energy between when the lump isn't there, we put a capacitor in. And we get that. Two things happen. First of all, ripple. The capacitor charges and discharges and charges and discharges. And as it does so, the voltage in the capacitor goes up and down. When the capacitor's charging, then the ripple rises as the capacitor charges. And then as the voltage tails away, the voltage from the capacitor, the energy is released out of the capacitor, and we get that long slope in the ripple. But also, don't forget, when we switch it on, we get this inrush current When we switch that circuit on, that capacitor isn't charged. And so there's a rush of current into that capacitor, limited only by the so-called ESR, the equivalent series resistance of the capacitor, which is typically a few ohms. And so you get a whoosh of current in there. And that can blow fuses, it can blow bridges, and it can blow transformers. So you have to design against that. It's even worse with a switch mode supply or a DC to DC converter. They will output ripple as well, but it's not 100 hertz ripple. The ripple from a rectifier and a transformer is 100 hertz. Those bumps are 100 times a second. Hum, have you ever heard the brrr hum that you get picked up on audio equipment from your fingers or from it not being very well connected? You've got a loose wire somewhere, you hear that brrr, that's 100 hertz hum. If it's a switch mode supply, that hum can be 50 kilohertz or 100 kilohertz. And that noise will go straight through a regulator. The regulator will give you 3.3 volts out, but it'll be 3.3 volts fluctuating with a ripple. And that ripple is hard to get shot of. It really is an issue. The easy way to do it is put a bigger capacitor in. But the problem with that is if you get a bigger capacitor, you get more inrush current and you're more likely to blow fuses or blow bridges or do whatever. The ripple that gets through the regulator will depend on the voltage, the current, the frequency, the temperature, a whole load of stuff, and you will see it as hum. If you don't hear it as hum because you don't have a speaker in your circuit, the I2C of your EZ bus or your CAN bus or DCC might hear it. That might manifest itself as a signal that's interfering with that. And I know there was a smashing thing on the forum this past couple of weeks where somebody was complaining about his old loco that it didn't work on EZ bus. And his EZ bus must have been wrong because this old loco didn't work. And after a fortnight of people telling them to try this and try that, replace all the wiring, get rid of that 10 base T and replace it with shielded armoured cable and good stuff like that, he eventually discovered that it was the old 1960s 00 that was putting out a whole bunch of noise, and that's what was interfering with the EZ bus, the I2C. So how to deal with this? First of all, if we increase the capacitor, then that should increase the problem. Sorry, that should increase the smoothing, but it also increases the inrush current. If we make the capacitor smaller to get lower inrush, that increases the ripple. If I put a resistor in there to make it the inrush be less, then that'll increase the ripple as well, and it'll cause a voltage drop. So that's not an ideal solution. There is an ideal solution, however, and it's this. Remember that transistor in the tail trick that I did with the Zener diode? This is the same trick, only this time it's with the capacitor. I've effectively multiplied the capacitance of that capacitor by 100. So instead of having a 100 microfarad capacitor, I've got a 10,000 microfarad capacitor, except for the inrush current. The inrush current still sees 100 microfarad capacitor, but the smoothing circuit, the rectification, sees a 10,000 microfarad capacitor. So I get the best of both worlds. And because it's a much less ripply input to my regulator, I get much less ripple out of the input. It's a circuit that you don't often see. It costs you one transistor and a resistor. But if you've got something that keeps blowing your power supply, think about that. It's a cheap and easy fix. Other ways that we have to protect against voltages. Back-to-back diodes is a great protection for an input circuit. You'll see this a lot. Let's have a quick burst. If I put two diodes back to back, that looks like a short circuit until you remember that diodes don't actually conduct until there's about 0.6, 0.7 of a volt across them. So that 0.6 or 0.7 of a volt is enough to be detected by the micro. So I now know that the input to pin 4 on that microprocessor will never see more than about 0.7 of a volt, which is great, because that's enough for me to detect it and get on with the job. Pin 2 has got the same circuit, only this time I'm using Zener diodes. And the Zener diodes have got an avalanche characteristic, so it'll be a slightly higher voltage that pin 2 will ever get to see. And lastly, the Schottky diodes, the ones at the bottom with that sort of swastika looking thing on them, are Schottky diodes. And those are exactly the same, except they respond so much more quickly. So where it might, a pulse of maybe a thousandth of a second might get through the diode clamp at the top, it won't get through the Schottky clamp at the bottom. So if I suspect I'm going to have spiky noise, high frequency noise, then I'll use the Schottky clamp, which is why if you look at DCC, where it's 100 kilohertz, 10 kilohertz, it's fast signals, you always use Schottky clamps to protect your circuits when it's DCC signals. Here's another one. This is a circuit that I use. I've got the spindle on my CNC machine has an output that's a pulse width modulated output to make the spindle go around at different speeds. However, as the spindle gets faster, the voltage also gets higher. So it goes for somewhere between about 6 or 7 volts up to about 20 volts. And I can't just take the spindle output and plug it into the laser. Sometimes the CNC machine's got a spindle on it for cutting printed circuit boards, milling printed circuit boards. Other times it's got an engraving head on it for engraving plastics or wood or whatever. So this little circuit takes the spindle signal and it uses that diode and resistor combination to make sure that this PIC chip can sense what the spindle signal is without seeing the voltage of the spindle signal. It gets a 5 volt signal that's the same frequency as the spindle, but always 5 volts. And it then analyzes that and uses that to make the laser signal that's most appropriate to that. So as I turn the spindle up, this goes up, but this circuit here makes the laser do something more appropriate. And that's another version of this. At a chip level, I've got some smashing stories about how electrostatic discharge works in the chip industry. And I suspect Keith has got some smashing stories as well. Mine's involve having to go out and ask the women in the line what type of underwear they're wearing and whether it was causing electrostatic discharge and all this good stuff. Most circuits have got a couple of really weird things that they do. First of all, if the voltage on one of the inputs, see GPIO 0 there, it goes into a MOS transistor. If the voltage on that transistor ever goes above the supply voltage, VDD, then the internal circuitry can turn into effectively an SCR, turns it into a thyristor that's short across the supply lines, and basically the chip burns out. So in order to protect against that, they put in a diode there. And that means if the voltage on that pin ever goes above VDD, then that diode conducts. And so it never gets to be above that voltage. And that means that the chip will never get an input that's higher than the supply voltage. And that's designed to protect the chip. So I had a problem. I was asked to investigate a number of years ago. This guy had designed something and it was intermittently, it was working great at switch on, and then after a few seconds it was stopping. And it was a microprocessor, a microcontroller, and we couldn't understand what was wrong with it. Traced out the circuitry, and after about 3 days of physically following wires with a pencil to work out what was going on, when he designed the printed circuit board, he had neglected to connect the supply pin of the chip to the supply. So the chip was never getting switched on, except when he switched it on, there were 5 volts on one of the supply pins. And so the 5 volts went through the supply pin, up through that diode and powered the chip. And so the chip worked. And it worked away till about 3 or 4 seconds into its initialization sequence when this input gets switched off. And when the input gets switched off, so did the chip. And the chip reset itself and it reset the circuit. And because he neglected to connect the supply pin to the supply, the chip was getting supplied via its input pins. And there have actually been cases of people designing chips and using this as a design trick. We will supply it through the input pins. It's not something I would recognise, but it's something to know in case you ever come across it. The same trick can be used with the diodes to make sure that your supplies come up in the right order. That 5 volt, if that 5 volt line there is higher than the 12 volt line, then the 12 volt line will get current from the 5 volt line until it's at least that level. And the same with the 3 volt line. So when I switch this on, I know that the 3 volt line will come up first, and then the 5 volt line will come up second, and then the 12 volt line will come up last. And that way I'm in control. Power won't get to the relays or the solenoids or the motors before the controller's up to control them. It's a trick that gets used in industry to make sure that supplies are happening properly. And so we leave voltage and move on to current. For protecting the mains current, there's lots and lots and lots of techniques. The most common is fuses. We all know about fuses. So-called fusible links. Piece of wire draws too much current and it melts. There's also all these other things, MCBs, miniature circuit breakers, earth leakage circuit breakers, residual current devices, RCCBs are the new ones. And every second year, the IEE changes the name of these things, and they all have to be changed, and we all have to buy new fuse boxes, except for my fuse box has still got ceramic fuse carriers on them. There's a soup of these things, and it's not my position in this talk to talk about them. There are people that are qualified electricians that can go through all this good stuff and keep us up to the 17th or 18th edition on that stuff, but I'm not doing it, and I'm certainly not doing it today. We do all know about fuses though. A fuse protects the wiring upstream of the fuse. If you put a fuse in a circuit, it is only there to protect the wiring that is upstream of where you just put the fuse. You should know about wiring ratings. Every piece of wire has a rating, a maximum current at which you should not exceed. Now that is not the current at which it melts, that's the current at which it becomes too hot to be safe. Right, so your house wiring is all rated at 30 amps, unless you've got a shower, in which case it's rated at 50 amps. Lighting circuits are rated at 15 amps, and so on. Crimped connections, I've already mentioned this in another talk that I did, but in America, after the Second World War, there was an enormous shortage of copper because of the war effort. And so they started doing domestic wiring with aluminium cables. They had lots of aluminium, and so we could make cable out of aluminium. But aluminium suffers from this weird thing called creep, whereby if you have a connection and it gets warm, or a piece of wire gets warm, then tiny fissures in the aluminium will migrate through the material, and they will migrate towards each other and coalesce, which means that the warm spot will get warmer, and as more it gets switched on and off again and the heat keeps going on and off, these little micro fissures will coalesce into bigger fissures which will get hotter, and eventually this thing will get sufficiently hot that something will burst into flames. And there was a spate of fires in the US from the 1940s through to the 1970s when they finally outlawed non-copper wire, and all this aluminium wire get taken out, and from then on all new builds were done with copper, and it was a genuine fire risk. Speaking of which, If you ever get anything from our Chinese friends and it's got a mains lead, then I implore you that you take that mains lead and cut it up and put it in the bin. Don't just put it in the bin in case somebody finds it and takes it out the bin. Cut it up so that if they find it in the bin, it's got no use to them. A lot of the Chinese wire is aluminium wire coated in a drawn copper coating, so it looks like copper, but it's not. If you take a piece of this stuff and hold a lighter underneath it, it'll retract, it'll sort of shrivel up and retract away because it's aluminium wire, it's not copper wire. If you take a piece of copper wire and hold a lighter under it, it'll just get warm. That's all it does. But this stuff shrivels away and it is potentially dangerous. Getting back to that thing about protection. This here is the new pocket money project that we're currently working on. Davey won't let me let you see this circuit, but we are currently working on it. There's a lot of good stuff there for you to look forward to. You'll be getting probably one of these in your Christmas stocking this year. And that circuit is driven by a wall wart. And the wall wart has a fuse in it, F1. And that fuse, F1, is only there to protect the bit of grey wire above my head. Right, that's what F1's for, that bit of grey wire there. And that's all. And the fuse itself, the cartridge fuse in the plug, which has got a 5 pointing at it, for reasons that I can't remember, I think there was drink taken when I was doing this slide, the cartridge fuse is there to protect the wiring in the wall. The 3 amp, 5 amp, 13 amp fuse that you put in there is to protect the wiring in the wall. The people put a 3 amp fuse in there if it's a very light device, that's fine. It means that if your device goes wrong, the fuse will protect the wiring in the wall earlier. It's not to protect your device. Your device will fry. But in the meantime, that fuse is protecting your house from burning down, not your circuit like this from going up in smoke. On the secondary side, we have rupture fuses, which are exactly the same as the fuses that I just talked about. On the primary side, we have semiconductor fuses. We can limit current or we can interrupt current. Let's talk about them very briefly. Fuses, secondary side fuses, are a science to themselves. There are anti-surge fuses, time delay fuses, there are A fuses, there are F fuses, there are G fuses, there are a cornucopia of fuses, and they are very, very complicated, and they're not for me to go through here like this. If I started going through this, we'd all be here to 10 o'clock tonight. There's a ton of stuff in here. I've left 2 URLs there. The top one is a lovely document that Radio Spares produce, and it's a guide for practitioners, if you like. It's the basics of fuses and what kind of fuses you need and why you would use them. It's about 6 pages. It includes how to change or fix a fuse in a domestic fuse box that's got a ceramic carrier. You know, the ceramic carrier with a wee bit of asbestos that you're not supposed to get near anymore, how to fix them. The bottom of those 2 documents from Little Fuse is a guide for engineers. It's 30 pages of equations and diagrams and graphs. That graph there is taken from the Little Fuse document. It's a smashing document to have if you're actually a design engineer and you're going to have to do this good stuff, then that's a document to have in your arsenal. But the top one, the Radio Spares one, is as good a document as any, and I recommend it. If you want to know more about fuses, you'll find enough there to get you by. The Polyswitch is a wonderful thing. These have been about for about a decade now. It's actually a thermistor, just the same as the big blue boys that we talked about earlier, except these are orange. Right? And I've got no idea, but they're all orange. Look at them, all orange. Same as the Varistors are all blue. And I don't know why the Varistors are all blue and the Polyswitches are all orange. I think it might be so that you can tell them apart. because these are effectively fuses, and you wouldn't want to put a fuse in where there's a varistor. A varistor's there to limit current. This would actually just blow. This is a little thing that you solder to the board. It might be a surface mount device, it might be a through-hole device. And if it goes over current, it will blow just like a fuse. But when it blows like a fuse, all you have to do is take away the fault, whatever caused it to blow, and then switch it off and switch it on again, and it's back. It's back in the room. The fuse is unblown. So if you've got a circuit that's liable to blow fuses, this is a great thing to have in it. You get them from about 6 volts to about 72 volts. You get them from about 50 milliamps to about 15 amps, and they'll cost about 50 pence, whether you buy a through-hole one or a surface mount one. You can buy them in tens from Farnell radio spares. You can buy, there's people on eBay will sell you them in 1s and 2s and 10s as well, but they'll charge you a wee bit of a premium, but then that might be worth doing. It might be something that Davey considers putting into stock as a merg item. And as I say, I've got no idea why they're always orange, but there you are. There's part of the data sheet. The little fuse catalogue for these things is fascinating reading. It's another 20 pager and it's got all sorts of graphs and stuff. There's what they look like when they're not actually blowing. Down where my head is, you'll see that the low voltage ones are typically 1/10 of an ohm when they're doing their thing. So in the circuit, you've put 1/10 of an ohm in series with your circuit. So it doesn't really affect your circuit until it comes time to blow. And then it becomes 2 megohms and you can assume that your circuit is safe. While we're on tables, put that one in as well to give you one of the big differences between these devices and varistors. They're PTC devices just the same as a varistor. But remember, the varistor, I said, takes 20 microseconds to absorb energy and do its thing. The varistor takes the energy, absorbs it, dissipates it away. This takes the energy, uses it to open a circuit and stays open as long as there's voltage applied to it. So it's subtly different. And the difference is to do with time. Look at the times to trip there. The varistors are measured in microseconds. This can be minutes. If you've got a high current, high voltage one of these, it can take a few seconds to blow. And so for that reason, they're not just as, if you need something to blow, definitely you maybe want a fusible link fuse, but for something that's not just that important, a polyswitch might help you. This is taken from one of the data sheets from the Polyswitch Manual, and I've highlighted 3 spots. This is one of the low voltage ones. This is a 6 volt polyswitch, a 6 volt semiconductor fuse. One of these ones that I'm telling you, you can just put onto your board. It's a 1 amp fuse or a 2 amp fuse, I think. And it takes 6 seconds to blow at that current. But if you give it 5 amps, it'll blow in half a second, less than half a second. And the lower of the 3 spots there, if for some reason it sees 20 amps, it'll blow in less than a beat of the mains, 8 milliseconds. A beat of the mains is 20 milliseconds, right? The one period of ripple is 10 milliseconds. So it'll blow quick enough if the current's high enough. If things are going badly enough for you, it will step in and do what it's supposed to do. This is one of my development boards for developing PIC circuits on. And how I supply it is, rather than put in a power supply or use a wall wart or any of that good stuff, I'm invariably developing these things in front of a computer, a laptop or a grandpa box or whatever. So what I do is I run a cable, just an ordinary USB cable from the grandpa box and plug it into the board. And the 5 volts from the USB will supply the board. Now, the 5 volts USB from a motherboard is supposed to fuse at about half an amp, or it's supposed to stop at half an amp, but I don't particularly trust that. So I've got a 200 milliamp 6 volt polyfuse in there, because on the PIC circuit, the pins for the supply and the pin for the 0 volts are right next to each other. And the pins for the 0 volts will have something like a scope probe or a meter on it, and it's waggling about, and it's liable to touch an input pin or touch a supply pin, and I'm liable to short something. Sure, the wee 6-pin header there for putting the PIC kit on, or for putting the FTDI cable on, has got the 5 volts and the 0 volts next to each other as well. And if those get touched, that's a short circuit. And I don't mind a short circuit blowing up a PIC, but I don't want it blowing up my PC. So for that reason, I've got one of these PicoSwitch fuses, in series with the whole lot. And to prove that this stuff works, this little thing is it's like an oscilloscope for current. And if you want to know about the oscilloscope for current, I will do that on some Sunday as a quick talk. It's a wonderful wee thing. It's a very, very useful tool. And I used that to monitor a circuit, and it was running away at 220 milliamps. And then I put a 1 ohm resistor straight across the supply. And as I put the 1 ohm resistor across supply, the supply shot up. And just before it got to 500 milliamps, the circuit opened and it switched off. I then reached over and unplugged it, and everything went back to working. Poly switches, wonderful tools. Limiting current. That circuit doesn't seem to have any current limiters in it, but it's got 2. One of them is the idiot diode. We've all heard about the idiot diode. There it is there. That diode is in that circuit so that if some idiot connects it the wrong way around, nothing bad happens. If I put the battery on there the wrong way around, then that diode is reverse biased, and so no current can flow in that circuit, and so nothing happens, and we're finished. Game over. The socket there is the second current limiter. If you notice the way that socket's wired, if I turn that socket round and put it in the wrong way round, pin 1 gets put on pin 4. So the earth gets put in pin 4 and the supply gets put in pin 2. And so again, nothing gets connected. And for that reason, the current gets limited to 0. That's the standard current limiter that we all use. The LM317 is a voltage regulator, but if you put it in series with a resistor, it becomes a current regulator, and you can limit current there. If you want to do it cheaper than the 317, or you've got a different current requirement, you can do that. The sense resistor there will be typically 0.6 of an ohm for 1 amp, or 1 ohm for 0.6 of an amp. And what happens there is, as the current goes up, that resistor turns on transistor 2, and transistor 2 turns off transistor 1. And so the voltage across that whole circuit becomes more and more and more and more. And so the current to the load is limited. If you were charging 18650 batteries, for example, you could use this circuit to simply limit the current into the 18650, and it'll limit the current to a sensible value until the voltage is reached, and then it'll charge at a constant voltage. Very, very simple current limiter. And go back to something that we did earlier on. If I've got a layout and I'm only running 1 loco on it, a couple 100 milliamps, but I've got a great big 5 amp controller. If I short the track, then that 5 amps is going to go through my short and blow the controller. If I put a very simple car bulb, that's the indicator bulb off the same MGB, in series with my controller, then if I get a short circuit across the track, the car bulb is a 12 volt car bulb across a 12 volt controller, and it brights up and we get to see the light. But when the track's only drawing 200 milliamps, the car bulb gets to see 0.3 of a volt or something. So it's 0.7 of an ohm Nothing happens. The car bulb is effectively not in circuit until it becomes a short circuit, at which point the car bulb will step in and save the day. If, however, my layout is suddenly running 2 amps, 3 amps, that's why I bought a 5 amp controller, because I'm running 3 amps in the layout, then the car bulb will start to put a significant amount of load on there and things will stop working. So it might be worth putting a car bulb in there with a switch across it. And the switch puts the whole layout into safety mode when I've only got one loco on and I'm setting things up. And once everything's working and I'm happy that I'm not going to get short circuits across frogs or anything like that, and everything's going to my satisfaction, I can throw the switch back into running mode and I can get the full 5 amps out of my controller. But I've got that as a safety mechanism. Current interrupters are electromechanical devices whereby when you put current through a coil of wire, that causes a magnetic effect. The magnetic effect moves a permanent magnet, which causes a mechanical latch, and that switches the current off, and then you have to reset it. You used to could buy these. You used to be able to go into the Electrovalue catalogue and you'd pages of them, but not anymore. I'll bet you everybody in this conversation though has seen one of these. See that red button there? When you shorted the track out, that little red button used to pop out. And if you drew too much current, that little red button used to buzz and go zzz when it was about to. And then you press the button in so it didn't short out and you push too much current. I remember, yeah, we've all done it and I'm not going to talk about it anymore. Not just so common though, is that one on the AVO meter. Or as anyone who's ever had to use one in anger on a job, particularly if you've ever had to carry one up a hill or up a mast, calls it the avometer. It's got a cutout on it just next to the 8 there. And that's designed to protect the mechanism, the movement. If the current going through the movement exceeds a certain amount, then that cutout pops out. It's the same electromagnetic cutout. The other place that you'll still see them is on the mains circuits supplying electrical mains, 3-phase mains in certain countries. Not in this country. In this country, we use reactors, which are great big coils of wire encased in concrete that are basically just inductors. And they're effectively, remember the bulb that I was using in series to non-linear device? That's what a reactor is. But in some countries, they still use disconnecting reactors to disconnect the part of the circuit that's drawn too much current. Lastly, for current, we get onto isolation. We should keep power wires away from signal wires. We should keep traction away from anything that's a bit technical. We can optically isolate circuits. And printed circuit boards. This is a printed circuit board for a switched mode power supply. If you look at the top, right now, without ever seeing the circuit for this circuit, if you look at the top, the mains comes in at the top, and you see these slots, you can see the holes. And through the holes, you can see the background. And you can see that apart from the round holes, there are slots, long slots, been routed in this board. If printed circuit board gets a bit of moisture or a bit of humidity, its conductivity increases, its resistivity decreases, and you can get arcing between the tracks. So in order to stop that from happening, we put a slot. Air has got much better characteristics in terms of as a dielectric or as a conductor than printed circuit board material has. So it's better to have air than it is to have PCB material. So you'll find that there's those slots, first of all, between the mains wires. There's slots to keep the mains wires away from each other and to keep the mains wires away from the low voltage stuff. There's also, you'll notice there's pads for putting in the varistor, but that's a whole other story. And then at the bottom, because it's a switch mode supply, it'll have a high frequency transformer, and that high frequency transformer will be prone to arcing as well. So there's a series of slots with the primary side of the high voltage transformer, which is on the right of the board, and the secondary side of the high voltage transformer on the left, with a slot down. And you notice the secondary side has got the solder flow over it. But you can see the slots to keep the transformer. In fact, you can see the 8 wires or the 10 wires for the windings of the switch mode transformer there. You can actually read that board without even knowing what it was designed for, just by looking at the number of slots and the thickness. The primary wires are thicker, the secondary wires are narrower because they're drawing less current, less voltage. And there's a whole science to printed circuit board design. Before I talk about printed circuit board design, I want to lastly talk about optical isolation. This is a trackside DCC decoder by Mike Bolton, one of the standard Merck kits. And I'm over to the bottom right. And if you look over there to the bottom left, you will see where it connects to the track. And if I zoom in to that bit of the circuit, you'll see that it has two optical isolators. One of them, the 6N series device, is a very fast opto-isolator. It's an opto-isolator that goes to a gate, so it's a logic level opto-isolator. The other one's just an opto-transistor. The opto-isolator that goes to the gate goes to pin 13, and that's where the pulses from the DCC are detected by the microchip in order to detect the signals that are on the DCC signal. He also has an ACK output on pin 12 that goes to U4, which is an opto-isolator. And when pin 12 of the circuit gets a 1 put on it, that turns on that LED of U4, which turns on the transistor part of U4, which shorts out that bridge, that diode bridge. And so effectively flattens the voltage on the DCC. So I take it this is an acknowledged signal back for DCC, maybe part of the Railcom system, or maybe part of a signaling system for letting the DCC signal send a signal back to the base. But the trick here is that it's all done without electrically connecting to the track. If you look, there's a gap there, an optical gap all the way down through that circuit, whereby the track over there is at no point connected to his microcontroller. So there's no choice, no chance of spikes or noise or crap from the track ever getting as far as the microcontroller. So he's not going to have to worry about debouncing or noise suppression or any of that stuff on that micro, because it's all taken care of by an air gap, an optical gap. Finally, on PCBs, I've already mentioned routing. In PCB talking, there's two words, route. You route tracks, you make them go from A to B, and then there's routing. You route slots with a router, which makes a hole in the board. And it's very easy to get the two words mixed up. I use route without an E for the whole thing, and route with an E for putting tracks down. You route slots for high voltage protection, to isolate high voltages and to keep the primary and secondary circuits apart. You space tracks far apart to keep voltages from jumping over them. You make tracks thicker to make them carry more current. If they're not thick enough for you, you either put a fillet of solder on top of it to make the circuit thicker, or you even put a fillet of wire on top of it to make the solder thicker to get more current onto it. You put lands and heat sinks. A land is, remember that area that was all covered in solder resist, big green area on the printed circuit board, that's what you call a land. And you'll very often put a land with vias, little connections between the two layers of the board to connect the two layers of the board. So you've got a great big lump of copper to conduct heat away. And you always design a printed circuit board, not against the circuit as it's supposed to work, but against the circuit when it's got a fault on it. If that was shorted out, where would the current be? Where would the voltage be? Where would the fire be? And that's where you design your board. You design your board as if it's going to be broken. Talking about thermals, we've got another couple of protection circuits first. This thing here used to be how you protected a relay. You put a capacitor across it to stop the spike, but nobody does that anymore. Two reasons. First of all, diodes are cheaper and easier, and you get better protection. It's called a flywheel diode. A flywheel diode means that if the transistor interrupts that circuit, the coil of the relay will try to keep the current flowing. As the coil of the relay tries to keep the current flowing, it will try to raise a spark. But the spark won't happen because the diode is in series with the spark, and if the voltage of the spark tries to go above 12 volts, current will flow through diode 1 to protect it. And that way, the spark won't find its way to the transistor, and it'll be protected. The capacitive trick worked initially, but people found that if you put a capacitor across and coil a wire, you sometimes get a resonance, and it caused as much noise as it was saving. And sometimes the spark itself was turning into the coil of wire, and the capacitor was turning into a wee transmitter, and you were getting electrical noise, which was causing more problems than it was saving. But they still use the capacitor across motors on locos because they don't know which direction the DC is going to be on the motor on a loco. And so they have to use a capacitor because it's a bipolar thing. You could use a bipolar diode, a diac. That's a discussion for some other time. Right, I am now a very expensive piece of equipment over here. Whoa. And that very expensive piece of equipment has to be protected at all costs. So I've got a circuit here that monitors it. It measures the voltage and it measures the current. And if it sees the voltage is getting a bit high, or the current is getting a bit high, it puts a pulse out on that wire to the left. And that pulse causes T1 to start conducting. T1's a thyristor, a silicon controlled rectifier. And when T1 conducts, it will blow fuse 1. It's like putting a crowbar across the tracks. And so it's called a crowbar protection circuit, a crowbar thyristor. And what happens is you detect bad things are happening and you just destroy the fuse. It's cheaper to replace a fuse than it is to replace the motherboard or replace this remote monitoring equipment, because it involves some very, very expensive gear or some very rare gear. Much easier to just blow the fuse. And so that's the crowbar. Much cheaper to destroy the fuse than destroy the gear. Thermal fuses are common in transformers and motors. Very often, if you look at a transformer, it seems to have there's something stuffed in there, something stuffed into the windings. And you pull it out and it looks like a wee fuse. And it is a fuse, but it's a thermal fuse. It's not designed to blow at a certain current or at a certain voltage. It's designed to blow when the temperature goes above a certain level. Thermistors can also be used in heat alarms as a thermal protection. We've all come across bimetallic strips to open circuits when they get too hot. And you sometimes still get wax capsule switches, particularly in fire alarms. So when the going gets too hot, the fire alarm melts, or the heat melts the wax capsule and the switch gets closed and the sprinklers come on or whatever. Thermal fuses are widely available. I went to Farnell and found 100 of them of different ratings. The only way I can tell a thermal fuse in a circuit from a fusible link fuse is its placement. A thermal fuse will always be placed somewhere that's going to get hot. It'll be in the windings of a transformer, or it'll be epoxied onto the side of a motor, or epoxied onto a piece of switchgear that's going to get hot. And that's the piece of equipment it's to protect. Usually the piece of the equipment immediately upstream of it, because a fuse always protects the upstream device. And so if it's a fuse, it looks like a fuse, but it's somewhere odd. It's not on a circuit board or on a fuse board or on a fuse box. It's maybe a thermal fuse. And that's it. But I'm finished. Thank you for your patience. I've run a wee bit over time. Any questions or any brickbats for me?